All right, okay, let's get started. So we will continue the chemical looping for ammonia synthesis. I think today we are going to talk about the microwave and also the microwave plasma enabled ammonia synthesis. So let's take a look at what we have done yesterday, and then so we just quickly summarize yesterday. Okay. Let's see. Okay. So I think if you recall yesterday, we talked about the first we discussed about background of chemical looping, beginning with chemical looping combustion. Then based on the same theory, we basically we say, hey, we can use the same concept used in chemical looping the combustion for the nitrogen what do you call that, as a nitrogen carrier, and then do the chemical looping. So if you recall, we discussed about this, the flow diagram, how we activate nitrogen. Okay, that's what we did yesterday. And then we discussed about the two papers, thermally heated reactor. I think I sent this to Dr. Anand. You should receive the 3 papers. One is this, chemical engineering technology. Have you received it, the paper?
Yes, sir.
So for this paper, at the end of today, I want you to, everyone read this paper. There are 2 other papers. They are from my group, microwave and also plasma. But you don't have to read those 2 papers unless you have time. But this paper tomorrow, we are going to do a case study, and then we are going to do a calculation and see if you can come up with the same catalyst or reactor size. Okay, so but I will talk about this at the end of today. But I want to continue today's discussion. So the chemical looping, this is using the manganese to synthesize the ammonia at ambient pressure, and also they use sodium as a promoter. So yesterday we discussed about this, and also we discussed about this is the graph from the book, the equilibrium conversion at a different pressure. This pressure from ambient to 10 bar, 30 bar, 50 bar, 100 bar. You know, this is when you increase pressure, the equilibrium conversion increase. But at ambient pressure, yesterday we mentioned at ambient pressure, you can only do the conventional Haber-Bosch approach. You have to operate at 200 to 400 degrees C. Beyond 400 degrees C, you don't have conversion because the thermodynamic limitation. You have to go up the pressure. But the chemical looping, we are able to operate ambient pressure because the chemical looping does not subject to equilibrium control. Hydrogen and nitrogen, they are not putting together in the same vessel. Okay, so this is a summary if you learn from yesterday. And also we talk about how you activate the N2 yesterday. So they call the nitridation. So the nitrogen carrier used in the chemical looping, it's not only has a catalytic function, but it's also using the bulk to activate N2. So the allow for the nitrogen on the surface, and also the nitrogen dissociated in the bulk. So we also talk about the competing the reaction, ammonia formation, or called ammonia harvest, and nitrogen desorption. So they are competing because you have nitrogen coming out, N2, you defeat the chemical looping purpose. You don't want the nitrogen come out, you want ammonia come out. And then that's what we discussed yesterday. And then so there, this one show in the paper. Now several cycles you can do. So I think this is going to be the homework I want you to calculate. So tomorrow we are going to go through this, read the paper, and then see if you can come up with the same calculation. So the paper says, to scale up a reactor, if you produce 100 kg ammonia per day, you need 1.2 ton of manganese. Okay, so the paper, I will point out how you, I will give you some clue, and then you can go do the homework, and then we can work together in the classroom. So we want to come up with, if we agree with this number, or we may come up with different number based on their data. Okay, based on the data in the paper, and then we will do the calculation together tomorrow. Okay, it's going to be case study. And then we mentioned about the ammonia yield reduction. I mean, this is theoretical chemical looping, but it depends on material. But most of the time, material will not be this stable. So that means there's declining. When you're declining, what's happening? So there's some kind of solution on this. So the declining means the morphology. I think yesterday one of the audience said, yeah, the material stability will be issue. Yes, this will be ideal situation. That means if you really have a chemical looping, you want this. But unfortunately, I think chemical looping, as we mentioned yesterday, is just follow something like this, a drop. So you want something like this, stable, flat. So then we have some, and then there's some evidence. You can see the morphology change, from the left to the right, and then for cycle 1, cycle 2, cycle 3. So basically, the structure collapse. Structure collapse means if you have the nitride in the bulk, and then the nitride coming out, so whatever the structure holding by this black dot, in the bulk structure, they collapse. So that's the problem chemical looping. This is different from the catalysis. Catalysis doesn't use any structure in the bulk. Catalysis is always happen on the surface, but chemical looping is different because this material is also the reactant. They participate in the reaction. So if you harvest all this black dot, which is nitride, then it's subject to the material the damage. So that's the trade-off. So there's some engineers. So I think yesterday we basically we left at here. So do not deplete nitride in the looping process. Okay. So what does it mean? That means if you deplete all this black dot nitride in the structure, it will end up like this. So structure will change. You can see from the left to right, and then the structure change. So when structure change, the nitrogen carrier deactivate. So do not deplete it. That means keep some of this black dot nitride still in the structure. You only let maybe half or 30% coming out, then do the next cycle. So you will hold this structure, and then it will not be damaged. Okay, so that's one of our engineering solution. True, it's always you can always develop the stable material, but that's really a lot of the research and development work. But from engineering side, this is one of the solution. Do not deplete the nitride in the looping process. So there will be structure damage. And then we talk about the chemical looping. It's different from the traditional catalysis. Traditional catalysis surface reaction, but chemical looping bulk material participating in the reaction. So there's a shrinking core model, which I'm going to talk about today. What is a shrinking core model? In the paper, they also mention about shrinking core model. Which paper? The paper I sent to you yesterday, this paper. Okay, so chemical engineering technology, they mentioned about the shrinking core model. What's a shrinking core model? That's what we need to talk about today. It's very popular in chemical looping. Okay, so shrinking core model. Okay. So what is shrinking? Before this shrinking core model theory developed, let's take a look at the traditional catalysis. Okay. So if you have a traditional catalysis, okay. So this is basically the surface of the catalyst. So I'm going so this is surface of so this is basically the surface of catalyst. So this is surface catalyst. So today I'm talking about traditional the catalysis. You have N2, okay. So the traditional catalysis means you have diffusion. I'm gonna put a number here, okay? So basically, numbers is 1, 2, step 1, step 2, step 3. So I hope you learned this theory before, but I'm gonna fresh your memory. If you haven't learned, just follow me. The step 1, 2, 3. So step 1. So step 1 is called the diffusion. So diffusion means external diffusion, gas N2 diffuse to the surface, and then there's internal diffusion. That means the surface has a morphology. So then the diffuse on the surface. Okay, so diffusion means external and internal diffusion. Then step 2, surface reaction. No, step is not surface reaction. Adsorption. So basically the molecule adsorb on the surface, and this step 3, step 2 and 3 are on the boson surface. Very important. So if you learn catalysis, trying to apply the catalysis to the shrinking to the chemical looping, it won't work. That's why they have to develop the model called shrinking core model. Okay. So basically the adsorption, and then step 3, surface reaction, and step 4, desorption. Desorption means after the surface reaction, the desorption disappear. So then they go to gas phase. So this traditional process, okay, N2 diffuse on surface, and then adsorption, surface reaction, then desorption. Okay, so this is the, if you read any literature, so basically it will tell you a couple steps. So okay, now let's take a look at what is the shrinking core model. Okay, so Anybody understand what I'm saying here? I just want to make sure. So I'm going to move this to the bottom steps. Anybody have any questions about the traditional catalysis? Okay. All right. Let's take a look at shrinking core model. So how does shrinking core model say? So shrinking core model is like this. I'm going to borrow the structure from the paper. Okay, let's borrow this structure. Okay, I think this is probably better. So the shrinking core model it's more like this. Okay, so I'm going to use this structure. Okay, the shrinking core model. God, it's not good. So just remember this structure. I'm going to redo this. Okay, so the shrinking structure like this. I'm going to do the same thing. So this is the shrinking core model.
Zero experience.
So shrinking core model, I'm going to expand it. It's not surface direction. It's a pop direction. So shrinking model, there are more steps. Okay. The shrinking model, I want you compare with the lab. So nitrogen, dissolve. Yeah, it's easier to teach in the classroom. I can just simply write on the blackboard. So there are 7 steps here. That's why I want to show you. So step 1, and then the modeling work on the shrinking core model is very complex. So you can see the it's a 7 steps. Okay, let's take a look at how the chemical looking the shrinking core model. Okay, step 1, it's the same thing. Okay, so step 1, I need to find a place to write this. Okay, let's begin. I'm gonna write ST1 means step 1. Okay, step 1, diffusion, external diffusion. the ST3, which is critical. Okay. So let's see if this makes sense to you, okay? Compared to the lab, which is the diffusion from gas phase to surface, adsorption, surface reaction, desorption, because the catalysis only happen on surface. But keep in mind that if you read this cartoon, and then the chemical looping happen not on surface, it actually happen in bulk. The shrinking core model, which is applicable to the chemical looping, step one, also external diffusion, because nitrogen has to come to the surface, and then the surface adsorption. That means the nitrogen has to adsorb on the surface, but that's not finished. And then the nitrogen actually diffuse into the bulk, step three, and the surface reaction means they react with the material and stay in the bulk. Okay, and then the number five, which is the desorption. And desorption means they react with hydrogen and then dissolve on the surface from the bulk to the surface, and then then they have basically the number five is so-called active site. So they react number four, step four, they react on the active site in the bulk, and then they have to dissolve from the active site. And then from the sixth, they have to go to the surface in order to leave the material, all right? So number seven, they disperse, okay? So this shrinking model is very popular, and then to describe what happened in so-called chemical looping process. So here's my question. From the step one to step seven, can you tell which step is could be the most difficult, or it's called the rate determination step, which means that step really limited the overall process. Can anybody just guessing what's the most difficult steps? Just look at the process. What's most difficult?
Reaction. Reaction in the bulk, sir.
Say it again.
Reaction in the bulk.
Step four.
Yeah. So step four, reaction in the bulk, because this is the hydrogen. Keep in mind, it's not just nitrogen. You have to have a hydrogen. The hydrogen come in. So I wrote the nitrogen in here. That's the formation of nitride. Keep in mind, the hydrogen has to come along in the same way. All right. So basically, once you adsorb on the surface, H2 in the chemical looping, the next loop, once this hydride formation, the hydrogen have come in. Hydrogen will go through the same process, and then but the only thing is hydrogen molecule is small. So hydrogen come in, react. So all this internal, the steps, yes, they are the most difficult one. The surface is really easy, desorption, and then come into it. So all this reaction on the side, it just depends on how you make material, how deep you penetrate the material. If you penetrate it deeper, that's the anyway. So shrinking core model, actually one of my I think the paper sent to you. If you look at the third paper, microwave plasma, I think my student she used she has the shrinking core model in that paper. I'm pretty sure it's in there, but it's a very complex the modeling work. Yeah, so in there you can see it's more complex than catalysis. Okay, so yeah, any questions? If you don't have any questions, we are going to move to the next because I think I have a lot of material to go through. So next today is Tuesday. So Wednesday, Thursday, Friday, 3 days, we have techno economics, membrane reactor, and also I'm going to talk about the hydrogen production. It's not electrolysis, it's the CO2-free hydrogen, which is the methane pyrolysis. And also I'm going to talk about also the microwave application in plastic for the hydrogen. If you know, ammonia is all about hydrogen production. We need to talk about clean hydrogen. So there are a lot of the topic we need to go through the next couple of days, and also we will have case study tomorrow and Thursday. So please ask a question, and then otherwise I'm going to move to the next one. So until this point, what we have talked about is a thermally driven chemical looking. That means the 700 degrees C, if you look at here, the 700 degrees C is driven by the thermal heating. So next I'm going to talk about same chemical looking process, but it is driven by microwave. Okay, so here's the topic. I think I sent you the paper, a Journal for Material Chemistry A, and then you already have that paper. If you are interested, read it. If you don't have time, I'm going to give you the high level lecture today on this microwave heated chemical looping ammonia synthesis. So first, you may be wondering why microwave heating. Well, we all know microwave is a selective heating, and then so in terms of the structure like this, let me copy it. So microwave is a selective heating. So if you look at the structure, you want the nitrogen come in to form this is the internal the nitride, all right? So this is really the good for microwave because microwave can selectively heat this site, deliver the energy to it. If you heat by the external heat has to heat all this manganese, okay? The manganese has to be the light gray, the white colored catalyst has to be heated, and then in order to heat the nitride. But microwave can come in, directly heat this black dot, the location. Okay, so that's the advantage. So the paper I'm talking about, actually they choose two different nitrogen carrier. One is the iron, the other is the cobalt moly. The reason they choose cobalt moly because it's bimetallic, maybe has more the selectivity under the microwave because it's bimetallic. The reason select iron is because iron has the not only the metal nature, they also have magnetic nature. If you remember, the microwave interaction with the material, it goes through dielectric heating, magnetic heating, and also the what do you call that conductive heating. So the iron will have you will see the data. Iron will have all of those, okay, because it's very sensitive under the microwave. So we kind of choose the two different material and to see, how they behave, perform under microwave. Okay, so the setup, again, this is the microwave only, and CLAS means CLAS means chemical looping ammonia synthesis. Okay, so we put into this reactor. It's continuous flow reactor. So microwave generator, and you have reactor tube, and then hydrogen nitrogen can flow through. So you flow nitrogen, and the next loop you flow hydrogen. So this is microwave heating. And the conventional heating is more like this. You have a tube, So this microheating because microwave, deliver energy. If you have conventional heating, it's also have a tube, but conventional heating, you basically, it's I would say this is a furnace. I'm going to draw the quickly how the different differences between the microheating. So this is the so the conventional heating. So you have the reactor tube, and you have heat sources, and then this conventional heating is convecting. Basically, you radiate heat onto the material. Okay. So microheating, you have the microwave field passing through the material back and forth. Okay. So passing through back and forth, and then it is the energy delivered as the electromagnetic field. Then they induce the heating. So it's target heating, slight heating. It's not really convective heating. And convective heating means you heat from the external to internal. Now the microheating is heating from inside out because from heating from inside out. So heat transfer actually from inside to the outside because it's the field delivery rather than convective heating. Okay, so this basic cartoon shows how we do the microwave chemical looping, and then we have also the IPR as the online analyzer. When ammonia shows up, we will analyze it by the online IPR instantaneously. Okay, so all the data I'm going to show you the next is coming from this the experimental configuration. So here's the result. I'm going to let you to take a look at it. If you haven't read the paper, it's from the paper I sent to you. So basically, this is caption of the paper. If you take a look at it, yellow highlight, this time on stream experimental data. Time on stream means that's 3 cycles: cycle 1, cycle 2, and cycle 3. And then using the different material. The label here, MW means microwave, and then the CT means conventional heating. So this graph actually compare the microwave heating versus conventional heating. Okay. The first cycle shows the iron catalyst. Okay, so if you look at label, the yellow, not yellow, the dashed line, which is the right dashed line, is the microwave heating. So the solid black line is the conventional heating. Okay, so essentially we compare dashed microwave heating. So microwave heating with conventional heating. Cycle 1, cycle 2, cycle 3. Cycle 1 means the chemical looping 1. You basically you absorb the nitrogen, and then you apply hydrogen, form ammonia. Then the next cycle that begins. So if you let me go back. Cycle 1 means you have nitrogen adsorption, and then followed by the hydrogen adsorption. So this cycle finish, ammonia produced. Then the next cycle begin, nitrogen adsorption and also the hydrogen reaction. Okay, cycle 1, cycle 2, cycle 3. So this is similar to this paper, but that's the microwave reaction we did in our laboratory. And the first row, the 3 cycles using the iron catalyst, and then the second row using cobalt moly catalyst, the same thing. Okay, so let's take a look at it. The iron catalyst, the right dashed line, in terms of the ammonia concentration. So obviously in cycle 1, microwave produces more ammonia in the entire operating range. So we basically run for 15 minutes. Okay, so 15 minutes. First we run the thermal, and then the thermal means we run this configuration. That's called the baseline, and then compare with the microwave. Okay, so the 2 scenarios. So you can tell the microwave using iron catalyst Fe is always better. Okay, so 3 cycles. So they can be regenerated and run again and run again, always better. Now when we change to the cobalt catalyst, which is the second row, the first cycle cobalt is much more active than in the microwave. But later on, the cobalt moly in the thermal become active. It's not because active, because the cobalt moly is kind of deactivated. So cobalt moly only active in the first cycle, but later on is not active anymore under microwave. But under thermal, they are still active. So this means cobalt moly is very difficult to operate under microwave. You only run 1 cycle and disappears. Whereas the cobalt moly in under thermal, the first cycle is not that active, but second cycle is active, the third cycle is still active. So to say different way, some material, they are stable under conventional heating, and some is stable, more active under microwave heating. So the conclusion from here, if you look at the first row, is iron is very sensitive and more active and stable under microwave and better than the conventional heating. But if you change the material, turning the cobalt moly, you run 1 cycle, but next cycle it disappears. So why the activity disappears? That's because this is so-called a shrinking core model. That means it's just the structure collapse. So it's very difficult to maintain the integrity, the morphology. So I'm going to stop here. I want to make sure you understand because the next the couple slides even more complicated. So we try to study what's the active phase of this, because why deactivate, how we are going to make a stable the material. Okay. Anybody have any questions on this point? Any question? You understand do you understand this graph?
Yes, sir. We understand your explanation, sir. So one thing, yesterday we discussed about that lifespan of the catalyst, or we may take lifespan of that looping agent, what we are using as a base metal. So here in that graph.
Which graph? So you say yesterday, which graph? Let's go through the yesterday graph. Which graph?
No, yesterday we discussed that today you projected it in graphs.
This one?
No, graph. The mic
This one? This graph? This one?
Yeah.
Okay. So that's your question. What's the question? Go ahead. So actually, let me try to understand your question. So basically this graph, this is a theoretical graph, and in the paper I sent to you, and then this is and the paper also talk about thermal heating. Today, we run the 3 cycles, use the same protocol. And keep in mind, this is a theoretical graph, okay? In reality, you may not have this. So now today, actually very good question. I will come back to here, okay? Let me copy. Okay. So it's a microwave. Actually, essentially, if you look at the graph, this is really similar. I mean, the shape of graph are different, but you have to look at the amount of the ammonia underneath, integrate underneath. Okay, so this basically shows there's no deactivation. Okay, so for iron cat is the right line. Now for cobalt it deactivates. So let me paste the structure here. So this is what you question, all right? So side by side. So the cobalt moly, the second row actually is more like this. It deactivates. Follow me? So yes. You run the 1 cycle, and the second cycle it disappear and disappear. This is the cobalt moly. But iron this is under microwave. But the under thermal it's stable. You see you have a thermal. So that means it's declining. It's what they say I'm gonna write it down. Okay, it's the cobalt moly under microwave. Okay, so this cobalt moly under microwave, this line is declining because they can only barely run 1 cycle. The second, third cycle, essentially they die. And then if you look at the iron catalyst, iron under microwave is more like this, right? It doesn't decline. Don't look at the shape. Look at the amount. You know, if you look at the area underneath of this the dashed line, it's essentially the same. It's more like this. It declines a little bit, but it pretty much is stable. It's the iron under microwave. Make sense? This right line. Is that what your question about the theory we discussed yesterday? And also now I show you 2 different material, iron and a cobalt moly. They behave different under microwave.
Yes.
Answer your question? Yeah.
Yeah. I got your things, right? And then in cycle 2, that left graph.
Which graph?
That left one, sir. Left one. No. The same slide, 17. Slide number 17.
17? Yeah.
Left one.
Yeah. Yeah, left.
Cycle 2.
Cycle 2? Yeah.
Chemical looping. In chemical looping, cycle 2. We could not find any peaks, sir. As per yesterday and today's session, the peak is coming. So in that graph, we could not find any peak.
Which or the second cycle, which graph you cannot find a second peak? Cycle 2?
Chemical looping, cycle 2.
Yeah. Cycle 2. Cycle. Look at my cursor. Are you talking about this cycle 2 or this cycle 2? This one, all right?
That one. Yes, sir.
Yeah. Okay. So you are asking why the shape of the peak are different. Is that correct?
Yes, sir.
Okay. Good question. So the shape of peak is the relevant to. Where's my diffuse? The shape of peak. So, but to answer your question, the structure does undergo the change, which means the shape of peaks is really relevant. This is 7 steps. So that means they are not highly reproducible. They are not highly reproducible. That means surface reaction, the peaks will be the same. But the bulk diffusion, this is step 2, 3, 4, 5. One cycle 1, cycle 2 to cycle 3, they may be different. The reason being that some of the structure already collapse. When some structure collapse or the structure become condensed, it's getting more and more difficult in the step 4 and 5. Because remember you mentioned, I asked a question, you mentioned step 4 and 5, they are the slow step, redetermination step. Actually, you asked a very good question. So step 4 and 5 may change because of structure collapse. So that's really reflected in here. So you have more peaks. So first one is easy, for ammonia to come out. And here, the ammonia come out and then drop, and then more ammonia come out. So you have 2 peaks. So that's all related to this shrinking core model diffusion. So yeah, very good question. And then later on become more difficult. The third, because they shows up as if they disappeared, and then another peak. That means you keep on releasing the I would say the bulk nitride. It just depends on how much you want to release. Ideally, you don't want to release so much. You just want to release probably 1 peak and have cycle started over again. Okay, so make sense? Yeah.
Yeah. Yes, sir.
Very good question. So all these peaks. So I'm glad I mentioned to you. I'm glad we discussed about this shrinking core. Shrinking core model. It's all related to the steps, and then all these steps. The internal desorption, step 5, step 4, the reaction, and then actually essentially 4, 5, 6. They are changing from cycle to cycle, because if any one step become difficult, which means when the structure change, and then you will see a peak. You see the 1 peak, and then see the 2 peaks and 3 peaks, because they try to, the basic microwave is selective heating, and then they try to push out the more ammonia as much as possible. So that's why they keep on coming out. The more coming out, the more the structure collapse. That's why from engineering the solution point of view, you probably, when we run this, we probably don't want to see 3 peaks. You want to see maybe 1 or 2 peaks, stop it, stop, and then go back to go to the next cycle. Otherwise, it's very difficult repeating. Okay, but in terms of quantity of ammonia, so the quantity of ammonia has nothing to do with the peaks. It's related to the area underneath. So if you integrate underneath area, this red line about the same. So it's just the steps how you produce the ammonia are different, because it's getting more and more difficult. The more peaks, the more difficult. I think that I'm glad you asked a very good question. So this is chemical looping. So you can model this. Actually, my student model this. So you can develop a model and then interpret and which step is which step is really dictate that process. Yeah. So you can feed all this data into the shrinking core model. Okay. Good question. Thank you. Should we? Yeah.
What you taken as you could not visualize properly. Ammonia, ppm.
Could you repeat the question again?
Yes. In that plot, y-axis. Yeah. What is the caption of y-axis? Y-axis. Yeah. Y-axis caption. ppm per.
You mean this reactor? heating?
No. Slide number 17. 17. That graph. Y-axis.
Well, you mean are you talking about cycle 3? The heating in cycle 3?
No, the unit which was used ppm per.
Yeah, I couldn't understand. I think the microphone has some problem. If you speak a little slowly, I don't understand your question. Could you repeat your question again? I couldn't hear clearly.
Sir, could you tell what is in that x-axis, that is PP, y-axis? Unit of y-axis.
Okay, you cannot. Why is it? It's ammonia. It's ammonia concentration. It's ammonia produced. So basically the.
Sir, could you explain what is that ppm per?
Okay. It's a ppm. So okay, good question. This is the y-axis. It's measured by. Very good question. Okay. Yeah. Sorry, I think that your microphone has some feedback. You have to speak very slowly before I can hear you. So that ppm is measured by the FTR. So it's a concentration. So when first you absorb nitrogen, then I absorb hydrogen. All right. So that ppm means very good question. Okay. So. So remember chemical looping, N2 become the metal nitride, all right? Then hydrogen come in, react with the metal nitride. There are some unreacted hydrogen, remember? So this FTIR analyze ammonia and hydrogen together. So that ppm concentration is how much ammonia in the hydrogen, the total. So that the higher the concentration, the better. The higher the concentration, the more ammonia come out. Okay. So yeah, that's what this analyzer tell you. And then this y-axis, yeah, I'm sorry you cannot see it. It's ammonia. It's ammonia concent. Let me read it. Yeah, it's ammonia concentration per gram of catalyst. So what does it mean? So that means there's catalyst in here, all right? So the ammonia concentration divided by the weight of catalyst in here. So basically we normalize it. So if you load 1 gram catalyst, how much ammonia concentration? Yeah. Okay. So that's catalyst. The catalyst means, yeah, I'm sorry. So okay. Cat, it means the catalyst.
Sir, we have one doubt, sir.
You got it? Yeah.
Yes, sir. Yes. Finally, one doubt, sir. Regarding
because I think I actually I tell the truth. I didn't pay attention to until you asked me. My student wrote this paper, and then I know that's the concentration of ammonia by FTIR, but I didn't realize there's catalyst in there. Yep. So basically ppm, per gram of catalyst. G means gram, and then the cat means catalyst. Yep. Okay. So yeah.
Yeah, we have.
Okay. You understand? Okay.
Yes, sir.
All right. But so I think that's a very good question. Now you see the difficult. So we have a 30 minutes break. When you come back, we are going to. I think I really want to finish this. Next will be plasma chemical looping, and then I'm going to spend half an hour, spend maybe 20 minutes to finish. Then we go to the next topic because we have so many things to talk about. So I want to finish this. We go to the next topic about economic and different absorption technique. So anyway, when you come back in 30, so we will take a break, 30 minutes, and then coming back, we are going to talk about we haven't finished the XRD on microwave. Then we are going to go to the another approach, plasma, then chemical looping. Okay, it's getting more and more complicated. I think I sent you the paper. This is from my student paper, plasma. But if you are interested, you can read. But let's talk after the break. Okay, see you. Yeah, 30 minutes.
Thank you, sir. Thank you, sir. We will meet after the break. ரொம்ப